Once again, good afternoon, everyone. I'm going to start the call. And some of you have submitted your homework already, and I'm going to evaluate them after this class. But I'm going to discuss the answers right now. I'm going to share my screen first. Okay. Okay, so I'm going to share my screen first. So this is the answer here. So I've noticed that, okay, I'm sorry. Most of you have answered like the second question. I'm not really sure about that, but I've done this in two ways. And I've also checked the answer key actually to this PDF. And the answer was this first version that I actually wrote. Most of you did it like the second solution right here. So the first one, most of you already did it correct. The formula and everything is already right. So I don't think I need to explain that since the formula and everything is pretty straightforward. So the first one, we have how many moles of hydrochloric gas are present. So want to find moles, we just use this volume divided by MR value. So I noticed that most of you use the STP number, which is a standard temperature and pressure. And hold on a second. So most of you use this one, like the standard temperature temperature and pressure. STP is going to shorten that, and that's like 22.4. That's the more value right there. But I'm using the RTP, which is the room temperature, which is actually the standard one that we've learned from the textbook. So that's why I'm using 24. So therefore, the volume is 1.20, right here, 1.2, as you can see it from the question. And we're going to divide that by 24. So therefore, we get 0.05 mole. Okay, so after we find the moles, we have the second question here. What was the concentration? So we know that the concentration, the volume concentration is moles divided by the volume. Okay, so the volume here, this is actually the volume of solution, okay, not the volume of the hydrochloric acid, but the dissolved here in the solution, which is water. And most of you already confirmed that 100 divided by 1000, so we have 1.100 in decimeter cube. So we change the unit from centimeter cube to decimeter cube. So we already find the moles here, which is 0.0500. We're going to divide that by 0.100. And therefore we have 0.500 mole per decimeter cube. So technically the one that I've noticed, the one that have submitted their work to me, I've noticed that you're already correct with this part. It's correct, but most of you used the STP value, which is 22.4. But I'm actually using the RTP, which is 24. And it's actually more common to use the RTP, though STP is, I don't think it's completely wrong. It's also correct, but it's more standardized using the room temperature. I think that's all, but all of you did well. It's pretty much the same like the one that I did right here. So do you have any questions about the homework? If you have any questions, just feel free to ask me about it. Before we move on to the next lesson, which is chapter 2, we are on to the next chapter, the new chapter. So do you have any questions?
Um, so, how do we how do we find the find
Yes.
the mole? Find the answer. Oh,
I'm sorry. How do you find the moles? Is that your question?
yes.
Okay, so how do you find the moles here? I think it's pretty much straightforward. It's right here. To find the moles, we use the volume of the gas, which is right here. This was dissolved by dissolved, I think you should call it. Okay, so that's the volume, which is 1.2. It's pretty straightforward, and it's already in decimeter cube, so we don't have to convert that. And we can divide that by the EMMA form at RTP. So this is the EMMA right here. It's actually pretty standardized. It's standard, which is 24 if it's at RTP, which stands for room temperature and pressure. Well, STP, the one that most of you use, I noticed that you use STP. STP is the standard temperature and pressure. So I do recommend using RTP, and the SOQ also use RTP, which is actually my first term. I use RTP as well. But then I kind of like think that probably STP can be another alternate solution, but it's okay, use RTP, and it's actually also what we learned from the textbook. We use RTP. And I think that what I can recall from my high school years, RTP is actually way more common in use rather than STP. So I actually haven't really heard much about STP back then. Most of when we don't know the formula here, we use these RTP here. I think that's what I can recall, and that's how you find the most, I guess. I hope that answers your question. If not, then could you yeah, you can ask again if you have any other questions or something that you want me to clear.
Nothing more.
Okay. Okay, so if you have no questions, I'm actually going to rewrite an explanation to each of you who submitted your work. Probably by this evening or tomorrow, then yeah, I'm going to re-explain it again in the chat. Okay, so that's all for this homework. Okay, I'm sorry. I think I stopped sharing my screen. I'm going to go back to our materials today. Since we're learning a new chapter, I'm going to reshare my screen. Okay, so we finished chapter 1 previously. So we're on to chapter 2 right here. Okay. So this is the learning outcomes. You can skip this part. Okay, so this is the introduction. Okay, so this is the introduction. Okay, I think I'm going to zoom this again. Okay, I hope this is not. Okay, so this is the introduction. Now let's explain how chemical substances behave. Scientists first had to understand what substances themselves were made from. Over time, a model was developed in which all substances were composed of atoms and elements. So this is just basically history. You can read this, it's not really important. This one is the important part. So elements and atoms right here. Every substance in our world is made up from chemical elements. These chemical elements cannot be broken down further into simpler substances by chemical means. A few elements, such as nitrogen and gold, are found on their own in nature, not combined with other elements. Those elements, however, are found in combination with other elements as compounds. Okay, so technically the one that we've learned from the periodic table, they're called elements. And when these elements combine with each other, for example, we have the most simple compound, which is we have water. So it's a combination of two elements, which is hydrogen and oxygen. So when it's combined, it will form a compound we call H2O or water. So that's the very simple example. F. And then here's the element. For example, right here we have carbon, the symbol will be C. And then we have lithium. It's actually derived from the Greek language, which is lithos. And therefore the symbol is L. So notice that most symbol in the periodic table, only the first letter is capitalized, unless it's a singular letter like this carbon right here. But if not, then it will follow by a lowercase letter. For example, here lithium. The I here is in lowercase. And there goes for iron, it's Fe, it's from ferrum, and then potassium is from calcium. And in Indonesia, we also said calcium, we don't say potassium. It's the same. Okay, so chemical elements contain only one type of atom. An atom is the smallest part, an element that can take part in a chemical change. And atoms are very small. And the diameter of a hydrogen atom is approximately 1 to the point of negative 10, I think. I'm not really sure how to read power number there. So the mass of the atom is usually a single hydrogen only weighs about this kilogram. Okay, so there's not much here. So now we're going to learn about inside the atom. And before I continue, do you have any questions about the previous explanation, or do you have probably something to ask about the periodic table or the elements? Because I think we are going to have a test, I recall about next week. So you can ask me as much as you want, and all I can say that I will include chapter one, the one that I previously taught, and then also about the periodic table. And it's not really hard. The periodic table is actually the basics that we've learned from our previous classes. So yeah, if you have any questions, just feel free to ask.
Uh, so what is the weight atoms weigh?
Pardon? What is the
What what is the atom weigh?
what is the what wait?
The
Okay.
atom weight.
The
What is
atom.
atom weight?
Atom weighs.
Oh, what is the atom weight?
Yes.
So I think atom weight, they're actually pretty much range. Um, so for example, right here, a single hydrogen atom weighs only 1.67 times 10 to the power of 27. I think it's 0.27. I think it's actually differ from each atom. I think if I recall that each atom weighs differently. Okay, so let me check, for example, what is a single atom of weight? Okay, so yes, um, the weight of each atom is actually it differs. Okay, so it differs. So for example, hydrogen is very, very light. It's 1.67 times 10 to the power of 27. While, for example, I've done my research here. A single iron atom is weighs 9.27 times 10 to the negative power of 26. So technically, the iron atom is heavier than the hydrogen atom. So yeah, it technically differ each atom. And if I recall that, I think here was like, okay, so it's actually technically differ, like I said, for each atom. So technically the gases, they actually have like lesser weight, meaning that they are not that heavy. For like metals, they like iron, they're actually heavier. I think I hope that answers your question. So yes, atoms are very, very light, but each atom have a different weight. So I hope that answers your question. So do any of you have any questions about elements again? Or if I haven't answered your question yet, then you can just ask me again.
No more.
Okay, so if you have no more questions, but if suddenly you think of a question, then you can just directly ask me, or you can just type it in the chat box, okay? Okay, so I'm going to move on to the next one. So inside the atom, the structure of an atom, every atom has nearly all of its mass concentrated in a tiny region in the center of an atom. It's called the nucleus. And the nucleus is made up of particles called nucleons. Just going to move on here. So there's two types of nucleon. There are protons and neutrons. And atoms of different elements have different numbers of protons. Also, the nucleus particles called electrons. So technically, inside the atom right there, so it has a center. It's called the nucleon. And inside the nucleon, it has protons and neutrons. Neutrons are the neutral. Um, it has a neutral charge, while protons have a positive charge. And then outside the nucleus, which is like around the nucleon, we have electrons. So they move around in radius of space, and they're called orbitals. And electrons, they are very light. It's actually electrons, they're actually lighter than protons and neutrons. And also it has a negative charge. So that's the difference. I think I've actually learned this from your previous chemistry classes as well. And chemists often find it convenient to use a model of the atom in which electrons move around the nucleus and electron shells. And each cell in a certain distance from the nucleus called particular energy level. So in a neutral atom, the number of electrons is equal to the number of protons. So if it's not equal, so you probably found some scenarios where number of protons and electrons are not equal to each other. So take this as an example. If an atom has more electrons than protons, then it has, and this atom will have a negative charge, or it's called an anion. So it will be negative charge. While if it's the opposite, if the atom actually have more protons than the electrons, then it will become a positive charge or a positive ion. It's called a cation. So that's basically the example of this one. So that's how ions are made. Basically, it's from an atom that has one of them is either like more protons or more electrons. So here is a diagram right here, so you can picture it better. So this one right here, the blob in the middle right here, we have the color red and the blue right here. The blue one represents the neutrons, which is the neutral charge. And then we have the proton here, the red color here. This is the proton, which is the positive charge. And it's just the middle right here. And the middle here, it contains proton and neutron. It calls the nucleus. And then around here, the orbital here, the large circle we have here, it's kind of like the orbital. And or you can say like the valence shell. So this is why it's called electron shell, the valence shell. It's actually the valence shell is actually like the very outer shell of the atom. And here, the green dot right here, it's called the electrons. It's energy level. And yes, the electrons they like move in certain ways around the nucleus. So that's um about the diagram. So okay, I think we can skip this part. So atoms are tiny, but the nucleus of an atom is far tinier still. If the diameter of an atom were the size of a football stadium, the nucleus would only be the size of a pea. This means most of the atom is an empty space. So electrons are even smaller than protons and neutrons. Yes, actually weight lighter as well, so the lightest amount of compounds. Okay, next we have here. So we can skip this. It's like about experimenting. Okay, so here's some questions. So question number one, a beam of electrons is passing close to a highly negative charge plate. When the electron pass close to the plate, they are deflected or you can say bent away from the plate. So here are the questions. A, what deflection would you expect, if any, when the experiment is repeated with beams of I protons and superprotons, neutrons? Explain your answers. And B, we had which subatomic particle, electron, proton, and neutron would deviate the most? Explain your answer. So I'm just going to give you some time to probably think about this about a few minutes, but that's okay. I'm going to explain it later. So it's just going to be like, yeah, you can just think about this first. I'm going to explain to all of you later. Okay, so this is based, I'm going to explain it to all of you. And if you're kind of like confused, then that's okay. I'm going to explain it. And if you have any questions, just feel free to ask. So this is based on what I've known or based on my understanding. So first of all, we have the first question, which is what deflection would you expect from the experiments repeated? Okay, so the first one with beams of protons and the second would be beams of neutrons. So we know that protons is a positive charge. So I assume that they would attract to the negatively charged plate. So they're attracted. So when they're close to the plate with the negatively charged plate, which is the electrons, these would be deflected towards it, meaning that it attracts each other since the proton is positive, right? And then the electrons, like the negative charge plate, it's negative, of course. So it will be deflected towards it, meaning it attract each other. So yeah, that's be deflect sorted. So the answer would be for the first question, it will be deflected towards. And now for neutrons. So as we all know, neutrons have no charge. It is neutral, and they would expect, I think we can expect that they will experience no deflection when they pass the plate, negatively charged plate right there. So since they're neutral, well, not going to be anything such as they're not going to be repelled by the electric field, or they're not going to be attracted as well since they are neutral. So the answer is no deflection for the neutrons part. So which subatomic particle would deviate the most? Okay, so this is actually really simple, I think. So it's pretty it's really an obvious answer. So the answer would be electrons. Electrons would deviate the most. And this is because electrons are way lighter than protons and neutrons, like I've explained before. And electrons and protons, they experience the same magnitude of electric force in the field. One is positive and one's negative, right? And the effect of that force will be greater in the electron. Why? Because electron has a much lighter mass compared to the protons. And this will result in a larger deflection if compared to the proton. Why? Once again, it's because of the mass. So neutrons would not deviate at all because they're neutral and it is not affected. So yeah. So we can actually cross out neutrons from this answer only. Why? Because it's neutral, it is the most stable among electrons and protons among the three options. While protons and electrons, well, they both have a charge, but first of all, electron is at the very outer shell, and then secondly, it has a way lighter mass. So that's why it defeats the most. So do you have any questions about this question right here? So if you have, just feel free to ask me, or if there's something that you find it confusing.
No.
Okay, so give me a second. I need to take. Okay, so if you have don't have any questions, I'm going to move on. But if suddenly you have like a question that you feel like you need to ask, then it's okay. Since we're probably going to have a test next week, so I really want all of you to really understand the material. So since we're actually also learning about atoms, but there will be no like mathematics for this atom part, only probably I'm just going to give a little spoiler for the test, for the exam. So, like in the first questions there's a bit about periodic table, and then about chapter 1 that we've previously learned, and probably some like questions. It's pretty similar to the homework that I gave you last week, the one that you just submitted to me. So it's actually pretty similar. So it won't be that hard, and the formula is actually just, yeah, it's the same. Just probably asking about like concentrations, calculate the moles or the mass of something. Yeah. So that's about this. And I'm actually going to make announcement later on, probably today or tomorrow. So masses and charges. So this is a summary right here. So electrons, protons, and neutrons have characteristic charges and masses. The value of these are too small to be very useful when discussing general chemical properties. So for example, the charge of a single electron is about this much. And we therefore compare their masses and charges by using their relative charges and masses. Okay, so here are the symbols. So electron, the symbols will be E, so this is just basically the first letter of the name here. And this is the mass, as you can see right here. So each, like the neutron weighs 1. Here too, when something, there's atomic mass unit, AMU there. And then the proton is also made as 1. It weighs 1. And then here the electron is really light, as you can see, when compared to the neutron proton. It's actually 1 divided by 1,836. It's very, very light. Yeah. So that's why, like, it's also the answers the first question. That's why it's really it can deviate the most. And as you can see, the charge neutron is 0 because it is a neutral charge, while electron is negative because it's a -1, and then proton is positive. Okay, so the number of nucleons. Oh my God. I'm so sorry about that. I think if like hear me disruption. Okay. So proton number and nucleon number. The number of protons in the nucleus of an atom is called the proton number. You can symbolize it as the Z. It's also known as the atomic number. So every atom of the same element has the same number of protons in its nucleus. It is the proton number that makes atom what it is. So for example, an atom with a proton number of 11 must be an atom of sodium. Okay, so technically, as you can see here, okay, I'm going to explain that later on, I think, for the questions, just to not make it confusing. Okay, so the nucleon number A is the number of protons plus neutrons, is the nucleus of an atom. It's also known as the mass number. I think we also learned this from previous classes, so I hope that you can still recall this material. So how many neutrons? So this is the formula to calculate neutrons. So the nucleon number equals to the number of protons plus number of neutrons. Then the number of neutrons would be equals to the nucleon number minus the number of protons. So it's basically A minus Z. Here we have, for example, an atom of aluminium has a nucleon number of 27 and a proton number of 13. So basically the nucleon number here is the mass. Usually you can say that. While the proton number is usually the atomic number at the very top. Usually, there it is. So it can be the proton number. So the atomic number is equal to the proton number. If it's 13, then it's 13. If it's 11, then it's 11. And then the mass right here, to find the neutrons, we have to just subtract the mass by the proton number. So here we have 27 minus 13, then we have 14 neutrons. Okay. So you have right here, use the information table to deduce the number of electrons and neutrons in a neutral atom of. So okay, about questions like this. So for tonight, I'm just going to explain that, like we're just going to discuss this directly. I'm not going to like make this as an assignment, but probably next time, like about a few weeks later, that I'm going to make this as your homework. But it's not going to be hard, I promise. It's really simple. All you do is just like a simple subtraction. Okay, so right here we have the nuclear number and proton number. So it's actually really simple. We only also deduce number of electrons and neutrons. So this one I'm just going to discuss this. Okay, so first of all, number of electrons. So we all know that when an atom is at its neutral state, like in the original state of an atom, then the photon number would always be equal to the number of electrons. It's, in other words, the same as the proton number. So it's really easy right here. So the electron number of electrons of vanadium right here is 23. Why? Because the proton number of vanadium is also 23. Therefore, the electron is also 23. Now to find the neutrons. Like the previous formula, uh, in order to find the neutrons, we need to subtract the nucleon number by the proton number. So we have 51 minus 23. So that would be equal to 28. So that's the neutrons. And same goes for strontium. The electron would also be equal to 38 since it's equal to the proton number. And then phosphorus as well. The electrons is equal to 15 as the proton number. And to find the neutrons is goes the same. Nucleon number minus proton number. So 84 minus 38, we have 46. And then for phosphorus, we have 31 minus 15, then we have 16 as the neutrons. So do you have any questions so far about the two questions here, about question number one, question number two, and also about to find the neutrons?
What's the table for?
What is this table for? So okay, so actually really serves no really much purpose about this. So the table is actually used for just to make things more clear between the atom, nuclear number, and proton numbers. Just make it more organized. So that's the usage of the table. For example, right here we have vanadium. It's just more easier to see as we can see what is the nuclear number of vanadium. We can see this right here is 51. So that's the usage of the table. So I hope that answers your question.
So how make an information in a neutral atom from the table?
So how can we pardon? So how can we deduce if the atom is neutral? Is that your question?
Yes.
Okay, so how do we deduce the atom is neutral? So basically, we're just going to assume that the atom is neutral because it doesn't state that it is an ion, right? It's only stated the number of electrons and neutrons in the neutral atom. So yes, okay, I never mind. Pardon me. There is actually stated here in the neutral atom, meaning that we don't have to deal with ions. For example, like one of them probably has more protons or more electrons than the other. But since this is really in the beginning of the chapter, so yeah, it's neutral atom. Probably about the ion, I'm going to explain it later in this chapter. But yeah, it's stated here as neutral atoms. So when it is neutral, we can just directly subtract the nuclear number by the proton number and we can get the neutrons. So I hope that answers your question. And also, once again, I'm just going to add, if the atom is neutral, then the number of proton will always equal to the number of electrons. So we don't have to do any um kind of like mathematics equation again because yeah, it's neutral. So proton equals to electrons in the neutral state. So I hope that answers your question. And do you have any questions again? Or do I need to explain things more?
No more?
Okay, so none of you have any questions? Okay, so since none of you have any questions, so now we're going to move to the isotopes. I don't think I think I'm am I going too fast? I hope all of you can catch up with what I'm explaining. If not, then you can actually just ask me, then I will go back to the previous materials if there's something that you would like me to clear up, okay? So here we have isotopes. So all atoms of the same element have the same number of protons. However, they may have different numbers of neutrons. So those same element that have differing numbers of neutrons are called isotopes. So just take note of this. This is a theory. So atoms right here, take note. So isotopes are atoms of the same element with different mass number. So they have the same element. They also have the same number of protons, but they have different number of neutrons. So just take note of that. So they are called isotopes. Mm. So isotopes of a particular element have the same chemical properties because they have the same number of electrons. They have slightly different physical properties, such as small differences in density. So they can differ slightly. It's a little bit different due to the different number of neutrons. So we can write symbols for isotopes. We write the nuclear number at the top left and the chemical symbol and proton number at the bottom left. So for example, right here. So the symbol of the setup of boron right here, we have 5 protons. We're going to write that at the bottom. And then 11 nucleons will be written at the very top. So hydrogen has 3 isotopes. The atomic structure and isotopic symbol for the 3 isotopes of hydrogen are shown in this figure. Okay, we're going to check that out later in the next page. So when writing generally about isotopes, chemists also name them by omitting the proton number and placing the nucleon number after the name. For example, this hydrogen can be called hydrogen 1, hydrogen 2, and hydrogen 3. It's pretty simple. Right here. So as we can see right here, um, we have hydrogen right here. As you can see, the number at the bottom right here, 1, 1, and 1. So these are the proton number. As you can see, the proton number stays the same, which is 1, while the number at the top right here, which is the nuclear number, they're different. This one, we have 2 and 3. So one we have here is called protium. We have 1 electron and 1 proton. And for the first one, for hydrogen 1, it contains 0 neutrons. It just contains 1 proton and 1 electron. But right here, on the second one, we have deuterium, hydrogen number 2. We have an additional neutron. All right, so that's what happens. And for the third one right here, which is hydrogen number 3, we still have the same 1 proton, 1 electron, except we have an additional of 2 neutrons right here. There we go. With this 2 neutrons right here, now it has 3 nuclear number. Okay, so you probably asked why this one has like 1 nuclear number, because 1 electron, 1 proton is basically become neutral, so it's considered as 1. But it still has no neutrons. And yes, the neutron, I don't really think that neutrons change the charges, because once again, neutrons are neutral charge, meaning that they have no positive negative charges. Doesn't really affect how the atom have negative or positive charge. It just affect probably the density and other characteristics, but they're not really significant usually. So that's the difference for isotopes. So do you have any question about isotopes so far, about this different structure of hydrogen?
No.
Okay, so if you have no questions, I think chapter 2 is a really short one. Okay. So isotopes can be radioactive or non-radioactive. So basically radioactive, I think you've learned this before, and I've really explained that radioactive, it can be hazardous, is all. So specific radioisotope, isotopes, radioactive isotopes, radioisotopes. Yeah, just eliminate the active there. It's kind of long. Can be used to check for leaks in oil or gas pipelines and to check the thickness of paper. They are also used in medicine to treat some types of cancer and to check the activity of the thyroid gland in stroke. So this is just another theory. So you use the predicate table to help you write a sort of symbol for the not following neutrons. Okay. So should we do this? I think we should do this. Yeah. So since we're going to move on to the next part, I think we're just going to do this right. Yeah. So I'm going to give you probably some time, about 2, 3 minutes to think about this, and we're going to discuss this before we end the class, right? Okay, so for question number 3. Okay, so I've just checked actually. Um, After this, we're probably going to end chapter 2 really fast. So that's why I'm just going to discuss like question number 3, and then we're going to move on to question 4 next week, probably, or the week after. We have a test. We do have a test next week. Okay. Okay, so I'm pretty much forgetful. So now we're at page 39. So I'm just going to check right here. So please take note, and if you have any probably periodic table, whether it's on your phone or you have just the physical, or you can just use that. So I'm going to see. So we have bromine, which is Br right here. We have calcium. So I think bromine we have calcium, and then iron, which is Fe, and then palladium. Palladium would be Pd. So I don't really remember the atomic number. Okay, so we have right here the periodic table. There we go. Okay, so we're going to see right here. So we have Br, which is bromine. We have 35. So the atomic, no, that's I mean the proton number would be 35. And then we have calcium right there. That would be 20. And then for iron or Fe, we have, okay, why does it doesn't want to state there? Okay, hold on. Fe, we have 26. And then for palladium, we have, what is it? Pd right here, 46. Okay, it's not upside down, right? No. Okay. So just go back here. Okay. So I'm going to write down Lucian, I hope. Okay. Oh my God. So I need to sign in here first. Right. So, never mind. So basically I can't sign in directly. Okay. Never mind. Hold on. I need to stop sharing my screen first. Okay, so give me a second. So I can just like write it down after sending in this test here. Okay. Okay, give me a second. It's still loading. So this may take a while, I'm sorry. I hope I can write under this. Okay. It's still loading. So give me a while here. Okay. So here I have a sketch for my. Okay, so I'm just going to reshare my screen. I'm sorry about the interruptions. Okay, hold on here. Mm, I'm going to share my screen again now. Sorry about that. Okay. So first question there, we have bromine. So bromine we can write as Br, which is the symbol. Br is the atomic symbol for bromine, and then we're trying to find the isotopic symbol. So we know that the mass number of bromine, which is 81, stated in the question. So we can write it like this, 81. And then we also can find the atomic number or the proton number on the periodic table, which that I found earlier, the periodic table. If you forgot, usually you can just look up at the periodic table. You don't really have to memorize every atomic number of the element in the periodic table. So here we have it, the isotopic symbol for bromine. And then for calcium, we goes the same. Calcium is Ca. And then we have the mass number 44. Going to write this right here. And then we have the atomic number B20 right there. So this is calcium. And then for iron, we have Fe. We have the mass number, which is 58. And the atomic number will be 26, or you can say the proton number, 26. So we also have palladium. So the mass number will be 110. And the atomic number, we have 46. Okay, so this is how to write isotopic symbol. First, we write the atomic symbol of the element, and then on the left, and then I mean the top left, we're going to write down the mass number or the nuclear number, and then the bottom left, we're going to write the atomic number or the proton number. So do you have any questions about writing the isotopic symbol so far? So don't really have to worry for the test. I'm not going to like bring out the isotopic questions. So you're really free. But yeah, if you have any questions, yes, feel free to ask. So do you have any questions before I end the class? Okay, since no one is asking any questions, so I assume that all of you understand today's materials, but if you still have any questions, you just can feel free to ask probably about next week if you have any. I think I'm going to continue chapter 2 again and then move on to chapter 3 for the next materials because chapter 2 we only have like one sub I think one sub paragraph. I mean like one sub chapter. Yeah, one sub chapter left before we move on to chapter 3. So it's still the same. Chapter 3 is still about atoms. So yeah. If any questions, just feel free to ask me. And then since none of you have any questions right now, so I'm just going to stop recording. Thank you everyone for participating in this class. And you can leave the meeting. Okay, I'm just going to stop recording.